Hello, everyone. We are going to look at example 7. We are interested in constructing a truth table for the following statement. We wish to do a truth table for the statement that says P and not P or not Q. So we always start on this statement. So what we know is we're going to need a table with a P, with a Q, with not P, not Q, and then we're going to need not P or not Q. So then let's do our usual truth table where we have T, T, F, F, and then we have true, false, true, false. Not P is false, false, true, true. Let me zoom in. Not Q would be false, true, false, true. Now we want to look at this. F or F is F, F or T is T, T or F is T, and T or T is T. So then we're going to look at P and not P or not Q. So then we're going to look at the following columns. And this T and F, T and F gives you F. So we're looking at F. Now, T and T is a T. F and T is an F, and F and T is an F. The only T is between T and T. So this would be our truth table. So there it is, F, T, F, F. And that's the solution that we got. And there is our solution, and this is the truth table. Now, when we're looking for the number of rows in a truth table, we always look at 2 to the n. The logical statement having n components, it would be 2 to the n. So if we have P and Q, it's 2 squared or 4. So we will have 4 rows in our truth table. Now let's look at an example. When we're making a several truth tables, some people prefer to use a shortcut method when not every step is written out. So there's alternate methods to constructing a truth table. We're also going to be looking at equivalent statements in the section. The equivalent statement is two statements are equivalent if they have the same truth value for every possible situation. So we can have two different statements have the same solution, even though they're different statements. And in order for them to be true, all of the solutions must be equivalent. Let's look at an example. We want to show that P, not P and not Q is the same as equivalent as the negation of P or Q. So then this is what we have. Now let's start with the truth table first of the following. P, Q, the negation of P, the negation of Q, and then the negation of P and the negation of Q. So the first thing we want to do is, of course, we know we have T, T, F, F, and then T, F, T, F, and then the not P is F, F, T, T, and not Q would be F, T, F, T. Now we want the and between F and F. False and false, we get false, false and true, false, true, and false is false, and then T and T is T. So F, 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 T, that would be our value. Now let's look at the or statement. So we're negating the statement P or Q. Well, let's look at P, Q, and P or Q. Well, we know this is T, T, F, F, T, F, T, F. Then the or, all of them, this one's true. This one's true. This one's false, false. Excuse me. When we're doing or, this is false. For or, this is true, 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 and false. The only one that's false is the last one. Now, if we're negating the statement, if we're negating P or Q, all you're doing is you're changing the original statement. So instead of a T, that's a false, a false, a false, and a true. Well, let's compare the truth values. So F, 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 T, F, 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 T. Yes, they are equivalent. F, 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 T, F, 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 T. Therefore, they are equivalent because we have the same true values that will help us identify the solution here. Let's look at De Morgan's law. De Morgan's law is as if you were distributing this negation. So for any statements P and Q, the following equivalences are valid. So when you have De Morgan's, you're distributing the negation to all, to the inside of the parentheses. So you negate P, you negate the quantifier. So instead of an or, it becomes an and you negate Q. So the negation of P and Q is negating P, negate the quantifier, and negate the value. So you're negating every single thing that's inside. So you're distributing, this is what I like to say, you distribute the sign or the negation in this case. So let's look at De Morgan. I got A or I got B. So it says A or B. I have A or I have B. So you're negating A, so you negate A and negating B. That would be De Morgan because you start with you have A or you got B. So A or B. Now you would not have A and you would not have B. That would be the negation. She will not try and he will succeed. So she will try and so instead of an and, it would be an or. So she won't try, so she will try because you're negating. Again, De Morgan says you're negating the statement. So you're negating that she won't try, so she will try. He will succeed, he will not succeed. And with that, we finish section 3.2. Thank you so much. Let's go on to 3.3. 3.3 talks about conditional and circuits. 3.3, the objectives of 3.3 is to recognize the structure of a conditional statement. A conditional statement is an if and if then Q. If P then Q. If P then Q. So we're going to have some conditional statements in section 3.3. We're going to be determining the truth value for conditional statements. So instead of a P or Q, it will be if, then. It has a different truth table. So we're going to learn about those truth tables. We are going to be expressing a conditional statement as a disjunction. So we're also going to, there is actually an equivalence between a conditional statement and a disjunction. They're fairly similar. We are going to be expressing a negation of a conditional. So we're going to see how do we negate a conditional statement, and then we're going to be using circuits to model conditional statements. So let's begin with some definitions. So a conditional statement is a compound statement that uses if and then. So our actually connective for this section is if and then. The conditional symbol is written if P then Q. It symbolizes as an arrow if P then Q, or P implies Q, if P then Q, or P is the antecedent while Q is a consequent. So we have all of these synonyms that go with the connective P then Q. So P implies Q, if P then Q, antecedent and consequent. We have our truth table. So our basic truth table is T, T, F, F, that's for P. Q is T, F, T, F. And then when we're looking at the conditional, it's the true, that's true, false, and true, then false gives you false. False and true is true. False and false is true. So the only false, this is the only false, is when you have T implies F. So TF is F. Everything else is true. So make sure we have this down in our notes. The only one that will be false is T implies TF is F. Let's look at this example. Given that P, Q, and R are all false, so they're saying already P, Q, R are all false, then find the truth value for the statement. So we're saying, so if P is false, Q is false, R is false. Now we want, well, what happens when we have F implies not Q? So F implies not Q. So not Q would be T. So not Q is T, not R is T, not P is T. So we have F implies T would be T, and then we have not R is T implies something false. So TF is F. So F would be our solution. Again, F not F is F implies T. F implies T is a T. T implies F is an F. So T implies F, that would be false. And that would be our solution when we are doing these type of values. Now, let's write this down. Special characteristics of conditional statements. So let's make sure we have this down somewhere. P implies Q is false only when the antecedent is true. So T implies F will always be F. That's because the antecedent is true, but the consequence is false. Now, if the antecedent is false, then P is automatically true. If it's true and both P and Q are true, then obviously it will become true. So these are some special conditions about this. Let's look at the next example. Here we have it. So decide whether each statement is true or false. T represents a true statement and F represents a false statement. Well, first you have T implies, is 4 less than 2? No. So T implies F is an F. 8 is equal to 1? No. So that's F. F implies F is actually true. So true and false. So again, T implies F is F. F implies F is true. Again, based on our truth tables. Now, what is a tautology? A tautology is a statement that's always true, no matter what the true values of the component. So that means that all of your, on that right side of your values should be true. So all of the components should be T. That's called a tautology. So this is checked by forming truth tables. So let's determine whether we have a tautology. So we want to show whether, and then here's a typo on my notes, but we want to say P or not Q implies P and Q. So let's see if that's true. Let's see if these are conditional. So here we have the conditional statement. This is a conditional. And then on this side, we have a conditional. Excuse me, that's a conditional, and this is a disjunction. Disjunction. So let's see if they are equal. Let's see if these are equivalent statements. So we have P implies Q first. So we know that truth value. So let me go back. Do you remember we have, it's going to be T implies, let me go back. So we have P, Q, P implies Q. So we have T, T, F, F, T, F, T, F. T, T is a T, T, F is an F, FT is a T, FF is a T. Now let's look at the other one. We have PQ. Let me actually change this. So PQ, not Q. And then we have P or not Q. So we have T, T, F, F. Let's find, so Q is T, F, T, F. And then not Q would be F, T, F, T. And then P or not Q. So T or F is T. T or T is T. F or F is F. And then F and T is T. So then here we have the value. So our TFTT or TTFT. And if we have P and not Q, so let's see P and not Q. So TF is F, TT is T, FF is F, and then FT is F. So then when we look at negation of P then Q and not Q. So we are going to have, there's a typo here. So here we notice that P or not Q, T, 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 F, 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 T is T, F, F is T. Now, T or F is T, T or T is T, F or is F. So these are not equivalent. Okay. Now we have a negation of if P then Q is also P and not Q. So we negate, if we negate P then Q, it should be Let's see if it's equivalent to P and not Q. Well, we already did P and not Q. We did F, T, F, F. And then let's look at the negation. If P, then Q. Well, we already have P and Q. We already have that value. T, F. So T, F, T, T. Let's look at the negation. F, T, F, F. Okay, well, F, T, F, 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 T, F, F. Yes, that is true. So the negation of P implies Q is equivalent to P and not Q. These are equivalent. So you may have equivalent statements or you may not. Now let's look at the next one. If we're determining negations, if I'm hungry, I will eat. So remember, what does that mean? If we are negating a statement, it would be P and not Q. So it would be P, you'll start if I'm hungry, then. So if I'm hungry and I will not eat. So again, if I'm hungry and I will not eat. All dogs have fleas. So you have all dogs and do not have fleas. So if a dog and it does not have fleas. So all dogs do not have fleas would be you'll start as a dog and it does not have fleas. So you're negating, you'll start with the first statement stays true, the second statement will be changed to a negation. Now, what happens when you write a conditional as an equivalent statement without using if and then? Can you do that? Absolutely. So if Indians win the pennant, then Johnny will go to the World Series. So what you need to do is actually define what P is and then what Q is. So P is the Indians will win the pennant. Q would be Johnny will go to the World Series. The Indians do not win the pennant, or Johnny will go to the World Series. Again, you're negating one of the statements and you're changing it to an or. So it'd be not, so not P or Q. So this is actually the equivalent as P and Q. So you negate P or Q. These are equivalent statements. So you had to negate P or Q. Now, the last part is talking about circuits. So circuits can be used to design electric circuits. So you have the P implies the Q and the Q implies the P. So we have a circuit P and Q, but we also have some circuits that might be parallel. So you have the P and you have a Q that might be parallel. You might have regular circuits or you have electric circuits that are actually defined by logic. So this is an example, and I have to reorder the circuits. Um, but here you have a circuit that is defined as you have a P implies a Q and not R implies not P or Q as so. Mhm.